So now in terms of a numerical example, well, obviously we need to have a Python program to do an evaluation of the state value function given a policy. So this is actually going to be called the prediction problem. Evaluate the VPy of S given a policy pi of A given S. Okay, so that is really the problem we're actually going to be facing. And we have introduced, if you like, the diagram, the tree representation of the problem. The tree representation of the problem involves starting from kind of some state and following a set of actions and expanding for each action all the other subsequent states that are opening up for us, we can actually go to. Given the grid world is a stochastic problem, it's a stochastic MDP, any action, let's take this action was to go right, starting from state S33. Okay, so for the state S33, if we are to go right, then following, if you like, the transition probabilities here, definitely we could go to S43. That's definitely a possibility with probability 80%. Definitely a probability of staying put on S33 with probability 10%, and definitely another possibility is to go over here with which is the state S32 with probability another 10%. Okay, so I think this is just running, if you like, that kind of program, seeing what kind of states we have, and potentially going in some kind of recursive fashion, as we have just seen in that kind of Bellman expectation equation, where if we knew the value functions of these states, we could actually go and estimate the value function of S33. So if I write the V pi of S33 for the specific action, which is to go right, then I am going to take some kind of some kind of instantaneous reward. Let's call it R plus gamma. This will actually be now a summation. This will actually be, so I'm transitioning, I'm taking any action, R, and I am actually, this is where I am given, if you like, this kind of action. I will be transition using a probability into one of those stages. Probabilities will actually end up being associated with my transition model. So this probability here is P of S43 given S33 comma A is equal to right times VP of S43 plus, I have another term here, P of S33 given S33 comma A is equal right times VP of S33 plus P of S32 given S33, the same thing, that will be the calculations that would have happened. So if we have fixed, if you like, the gamma to a value, let's say 0.1 or whatever, and we knew this kind of value functions, given the fact that the transitions are known, so this probability will be 0.8, this will have been 0.1, and this will actually be 0.1, then we would be able to estimate that kind of a value for that kind of state if we have to follow this kind of policy, let's say going always right. And now that we have seen in a little bit how that previous kind of equation that we have produced kind of is being used, it's worthwhile just going through now the Python code to see how this is going to be done. And so to understand the Python code, I think it's worthwhile mentioning the simplest possible way of actually solving this kind of a problem of the evaluation of the state value function is to observe that if we are to write all these kind of equations that we wrote for S33 for all states, all other states, then we're going to have as many equations as the number of states, and these equations are linear, so we can actually solve these equations for the unknowns, which are the state values. And that basically that's the end of the estimation process. Now, preferably, we do not want to use, I will call it any matrix inversions or anything associated with these kind of solutions associated with system of linear equations. Obviously, there are ways that we can solve this system without really this kind of numerical kind of complications. And one way that we will need to understand here for us to understand the Python code is the iterative way of solving these systems of equations, which is actually pretty common. So the equation we will actually be migrating to is the following. So I'm going to write down the equation. So it is V. I will define as small letter k as the iteration index. So V k minus plus 1 of S. It will be summation over A, pi of A given S, and summation of over S prime and R of the MDP dynamics, which is of course known, R plus V k of S prime. And this is known as the so-called iterative policy evaluation. And this is what is being used in practice. So we will be using this equation. Is actually very straightforward. In the Python code, you will see that the state values will be presented by a vector. So we have, let's say, 4 by 3, 12 minus 1, 11 states. And we have a vector of representing this V over here. And we start with some initial value on that vector, let's say all zeros. And we then, depending on which S prime we ended up to, we pick up that value of that vector to calculate this thing, and then we update that vector as we go. And we can actually do that in place or using two separate vectors. In the Python code, you will see two separate vectors, but you can also do that in place replacements. And therefore, just using, in other words, one vector for both of these states. You will see in the Python code, this will be called vnew and the other will be called vold. So let's go to the Python code and see what's happening over here. So the Python code is in the process of being migrated to a standalone code. So right now the code is sitting in line with the text under the section policy evaluation or prediction. And here we see the grid word that we have. We are using a library called Gym. Gym is a library that itself is evolving. So it's actually today is called Gymnasium. And given that we have already specified the grid world environment over here, which primarily is a class of all the associated entities in that environment, plus a number of methods, the most important of which is a step method, where the environment is transitioning, is giving us the reward and the next state. The policy evaluation function is really the main function of interest here. It takes as argument a policy that we have to evaluate, the environment specifics that we have instantiated over here, a discount factor gamma, and an epsilon that it will actually be used as part of a stopping criterion, because it's an iterative kind of algorithm, so we have to escape from that kind of infinite loop we have applied over here, given when we see that the state value function is as a vector, that state value vector is not really changing that much, so we can actually stop the iterations over there. So that's the what I explained as v old and v new. So we start with some value, state value function, which is an 11-dimensional kind of vector v that we call v old over here, and another 11-dimensional vector v that we call the v new, that is vk plus 1 and the vk, and that in the iterative policy evaluation equation. And we are actually looping over states to calculate first, based on the policy, the Bellman expectation. This is basically the equation we just wrote here, to calculate the elements of the v new. And if we are to progress, to proceed, then we are setting the v old is equal to v new in order for us to start another iteration and move into a more accurate state value function. So it can be shown that the iterative policy evaluation will reach, if you like, a vector of state values that it is identical to a non-iterative approach that if we had followed. And that is basically what we are reporting here. So we have we are trying to evaluate now a specific policy. It's called a random policy. Earlier we called it stochastic policy. Random and stochastic is one and the same thing. And that policy is a policy that it is defined here by, it's a uniformly kind of random policy. We are evaluating it and we're producing the output of which the non-iterative version will actually result into this vector of values, and the iterative one will result into a vector which is very, very close to those values if you run the code. I think I just quoted the number 11 to be the number of states that this Python code is responding with. But unfortunately, it is not associated with this grid world environment. The grid world environment that it is, this code is actually assumes, and that's why it returns, if you like, 14 states, is this one that it is presented in the Saturn's book, and that's actually the classic 4x4 grid world, where we actually have 2 terminating kind of states and 14 other states where we are able to act according to this equiprobable policy. So we can go up, down, left, and right with equal probability. And the immediate kind of reward will actually be -1 for all transitions. And therefore, effectively, what the Python code is actually doing is it is really giving us, as the k number of iterations progress, effectively it is converging into this table over here. So if you see the numbers in the Python code and the numbers over here in this actually table, which are also in your notes, they are kind of identical.